Welcome back, everyone. Recently we've been talking a lot about definite integrals, and the way that we evaluate definite integrals so long as the function is continuous is with the fundamental theorem of calculus. You find the antiderivative of the function and then plug in the upper bound and plug it in the lower bound. And most of the work here lies in finding that antiderivative. Sometimes it's easy to do if the function is like e to the x, for example, and sometimes considerably harder than that. So in this video and the next few videos as well, we're going to talk about how to find the antiderivatives of certain types of functions. Before we get to that though, I need to introduce some notation. And I want to remind us of one of the examples we did from the definite integral videos, which was that an antiderivative of 2x is x squared, because the derivative of x squared is 2x. But that wasn't the only answer to an antiderivative of 2x. We could have also had the antiderivative be x squared plus 1, because the derivative of x squared plus 1 is also 2x. And these are both valid antiderivatives, and you can imagine that adding any constant to the end of x squared would also be an antiderivative. And since these are all valid antiderivatives, we can represent all of these as once as the family of antiderivatives, and we call this x squared plus c, because that plus c represents any constant you could add to the end there, and so this really does represent all of the possible antiderivatives. And there's only one family of antiderivatives for any function that has an antiderivative. And the notation below is called the indefinite integral of the function f of x. And this gives the family of antiderivatives for f of x. And so it looks like an integral sign, but notice that there's no bounds on the integral. And this is an indefinite integral, and it gives you the antiderivative of the function plus c. And this indefinite integral allows us to talk about antiderivatives without having to evaluate at the bounds. Now I want to emphasize that the definite integral and the indefinite integral have two different meanings. The definite integral represents the signed area under the graph of f of x on a particular interval a to b. We've dealt with this a lot lately. We've seen the area interpretation before, and this definite integral, so long as it exists, gives you a number, whereas the indefinite integral represents the family of antiderivatives of a function, and so the output here is not a number, but it's a brand new function, or a family of functions. And this indefinite integral does not represent the area under the curve of the function. It really just gives you an antiderivative plus c. Now that we know what we're talking about, we can start looking towards how we can find the indefinite integral, which is really just the antiderivative plus c of certain types of functions. And all of these rules I'm going to show you are really just the basic derivative rules in reverse. For example, for the indefinite integral of a constant function, where k is a constant, the indefinite integral is kx plus c, because the derivative of a constant times x just gives you the constant k, and then the derivative of c is 0. For example, the indefinite integral of 3 times dx would be 3x plus c, and with all of these you can always check your work by taking the derivative of what you get, and you should get back to where you started. Now, one word on notation: if I have an integral sign and just a dx in there and there's no number, there's sort of an imaginary 1 hanging out in there. So if I have the indefinite integral of just dx, imagine that being the indefinite integral of 1, we're using this constant rule that's going to give you x plus c, because the derivative of x is 1. Next, we're going to move on to our best friend, which is the power rule. And if you recall the derivative of a power function, you move the exponent to the front of the power function, and then you subtract 1 from the exponent. And now that we're doing this in reverse, instead of subtracting 1 from the exponent, we're going to be adding 1 to the exponent. So the indefinite integral of x to the n dx is x to the n plus 1, and instead of multiplying by the exponent, we're going to be dividing by this new exponent that we get, which is n plus 1. And you could imagine taking the derivative of this. If I took the derivative of x to the n plus 1 divided by n plus 1, I would move the n plus 1 down in front, and I would be left with an x to the n, and the n plus 1 being multiplied would cancel out with the division of n plus 1, and I get left with x to the n. As an example, the indefinite integral of x cubed dx, I'm going to add 1 to the power, which is x to the power of 3 plus 1, and then I'm going to divide by that 3 plus 1. And you can just think of this as x to the fourth divided by 4, but I was just trying to be explicit here to get the idea of what I'm doing across. And never forget that plus c at the end. Now I could do something more exotic than just a power of 3, say the indefinite integral of x to the power of e dx. Well, it's still the same thing. E is still a perfectly fine constant. I'm going to add 1 to the constant, which is x to the power of e plus 1, and then divide by e plus 1, and then add c. And our last rules for this video will be the indefinite integrals of sums, differences, and constant multiples. And these are the same exact rules from the derivatives of sums, differences, and constant multiples. And we're just going back the other direction. So the indefinite integral of a sum of two functions, f plus g, is the sum of the indefinite integral of each. So I can distribute the indefinite integral sign to each function and then add those together. And same exact thing with differences, but there's a subtraction sign in the middle instead of a plus sign. And with constant multiples, if you recall the derivative of constant multiples, if you had a constant multiplied by a function, when you took the derivative, you would ignore the constant and then take the derivative of the function. And it's the same exact thing here. If I'm taking the indefinite integral of a constant multiplied by a function, I can ignore the constant and bring it out in front and just take the indefinite integral of the function f of x times dx. And notice this is not a constant on its own. This is a constant multiplied by a function. So it's different from the rule from earlier, which was a constant on its own. Now with just these rules, we can take the indefinite integral of any polynomial, which as you know by now, show up all the time. And as an example, let's take the indefinite integral of x squared plus 2x minus 3, all of that multiplied by dx. And notice that this is a sum and difference of 3 different terms, so I can use the rules from the last slide to distribute the indefinite integral sign to each term individually. And notice how each term, I'm still including the dx there, it is an important bit of notation that you can't leave off. Also notice that I brought the 2 out in front of the middle term because using the constant multiple rule, a constant multiplied by a function, I can ignore the constant, bring it out in front, and just take the indefinite integral of the function itself. And now I can look at each of these indefinite integrals individually, and the indefinite integral of x squared using the power rule, we're going to add 1 to the power, which is x cubed, and then divide by that new power, which is 3. And the same thing for the term in the middle. If I take the indefinite integral of x, I'm going to add to the power, which is x squared, and then divide by that power, which is 2. And that 2 out in front is the 2 in front of the indefinite integral that's still hanging out, and you're going to multiply that in afterwards. And finally, we're going to be taking the indefinite integral of 3 dx, and the indefinite integral of 3 is 3x, and don't forget the subtraction sign there. And at the end of all of this, you need a big plus c. And you don't need a plus c for each individual indefinite integral, because if I had 3 different constants, I could group those together, and the sum and difference of those 3 constants would give me just 1 constant. So I just need 1 constant at the end here. Now you could simplify that middle term if you wanted to, but you don't have to. This is a perfectly fine indefinite integral as is. Now as you get better at finding indefinite integrals, you don't need to show that middle step there where I distributed the integral sign to each individual term. You're more than welcome to do these basic indefinite integrals in your head.